Thank you very much. Thank you for invitation to give a talk here. So I'm talking about zeta functions. So zeta functions in general, I think, is a kind of guide from above to guide mathematicians to interesting new mathematics. And the one I'm talking about today, it's about Mathieu-Galois group, but the story starts from the classical formula. So if you have F is a number field, then there is a very classical formula that the residue at S equals 1 of zeta Fs equals something. I'm not going to introduce any of these quantities, except mention that this is the one I really care about. And it's given by a determinant of logarithm. So that's a regulator. It's a determinant of logarithms of absolute values of sigma I yj. Where these are units in our field. So this is very well known. Now, the question was, how about zeta Fn? And Zagier proposed a conjecture which tells the answer. We generalize this formula. And the first thing we want to know what's the analog of z. So the first question is, what replaces logarithm of absolute value? So this is the classical polylogs. Let me remind who they are. So this is just the functions on one variable, z, which is given originally by power series. And k goes from 1 to infinity and can be analytically continued by an integral by induction using a formula like that, where you integrate from 0 to some point z, missing the point 1. Now, that's not yet good because this is the n-log of log, but not of log absolute value. And the log absolute value is the following function. So it's Zagier's function. So you do this. So you write it's ln of z. It will be a single valued function. And it's defined as sometimes real part, sometimes imaginary part, real when n is odd, imaginary when n is even, of the following expression. That's a sum 2 to k bk Bernoulli number divided by k factorial when k goes from 0 to, let's say, n. N minus 1, n minus k of z times a logarithm k absolute value of z, absolute value. Now, here the point is that you use this particular path, not the other path, for all of them. You continue all of them along this path. And then if you take real or imaginary part, this single valued function. And if you deform the path now, then the value doesn't change. So you can cross now 1 in the definition of them. The value doesn't change. OK. So let me just say it. It's single valued. And generalize the famous Bloch-Wigner dilogarithm, which appeared about 10 years before that. OK, so now what Zagier's conjecture says roughly. So it roughly says that formula like that's supposed to be true. Again, the formula doesn't care about anything. The formula certainly doesn't care about rational numbers, doesn't say anything about them. It has pi's and square root of discriminant incorporated. But the main point is that it says that one should consider the values of n logarithm on some y, let me call them maybe xi's. So this xi's is just some linear combinations, maybe ai, some z. OK, I put already I, so let's just say a is sum of aj, zj. And so this guy lives in your number field f. And this is a rational number. And so the main point is what conditions these numbers have to satisfy. And so the conditions, there are several of them, the way Zagier put it. So the first of them is that if you consider the following thing, sum of Aj, then 1 minus, I put Z, Zj, wedge Zj, tensor Zj dot and so on dot Zj. So all this lives in exterior square of f star tensor Q, tensor n's minus second power of f star. All this tensor Q. So this is n minus 2 of them. So this expression, and this is a rational number. So this lives here, and this is just rational number. So you can sum elements in this Q vector space with this coefficient. So this must be 0. But that's not enough. Then there are some other conditions, so about m of them. And just to give you a sense what it is, so if you take, for example, when n equals 2, we already done. When n equals 3, there is a next condition that sum of Aj, the dilogarithm of Zj times the valuation for any valuation V of your field of this guy is again 0. And for high n, there are high conditions like that. So the first thing I wanted to do, I wanted to set a different.
Those higher conditions you can't formulate purely algebraically anymore.
You need the polar log for them. Yes. I'm going to formulate purely algebraical all this condition at once, just in a second. So, but in order to do this, so I want to introduce the main player of this lecture is a motivic polylogarithmic complex. And maybe to finish with that formula, with that discussion, so this is Zagier's conjecture, like almost formulated. So the statement was that if you consider determinant of this Langlands on some linear combinations which live in free abelian group generated by F, then and take all of the possible embeddings, appropriate embeddings, then the corresponding determinant will be either 0 or proportional to the special value of zeta function. And this, I'll tell you the precise formulation for n equals 4 later. But this was proved when n equals 2 by Zagier himself in 86. And also independently, it was proved by Bloch and Suslin and Varel before that, but the proof was kind of needed some extra, I would say 90. I said independently as a joke because it wasn't quite realized, but so Zagier proved this formula, but it also followed from results of these people, plus some epsilon, which was added in about 1990. And these results go to end of 70s, beginning of mid of 70s, beginning of 80s. Also, it is known for n equals 3. So I did this about 1990. And so what we're going to discuss today is n equals 4 case. And my main goal, first of all, to explain why do we care about n equals 4 that much? And secondly, what does it mean? OK, so let's go. Let's first of all transform the question to the area of geometry. So we talk about polymotive complexes. And again, whatever I'm going to say for the next few minutes, this is all old definitions and kind of setup. But I need to recall it to state the.
What's the statement?
Huh? What? What?
What actually was the statement?
You will see the statement in 10 minutes the way I want it. OK?
Does it include you defined a function before? You defined another function before?
I define the function and I say that if you take determinant, the rough statement is the determinant of some matrix, take ln of sigma I and this xj, this determinant is proportional up to q star and up to some standard factors to zeta f of n. That was the conjecture. If this xj satisfies some conditions. And these conditions were listed only for n equals 2 and n equals 3. OK? I'm going to tell you a different way to think about this and state the statement a little later. So now what's important that we take f to be any field, not number field. And so what you want to do, you want to define some groups, high-blow groups, which are defined as a quotient of a free abelian group generated by elements of your field F by some subgroup And this subgroup, morally, is a group of functional equations for Ln. So it's give you functional equations for this function Ln. And there is a little problem with that. The problem is that these functional equations are known very well known for n equals 2, n equals 3, and we know them for 4 and 5. And there are some other records, maybe 7, maybe 10. But if you take some number which is well above 0, for example, 20, then we don't know any of these functional equations except a very trivial one, that if you take ln of x plus minus 1 to n ln of x inverse, this is 0. This is the only equation which we know when n is bigger than 0, really bigger than 0. So still we wanted to define this subgroup, which can be done without naming them. So first of all, the subgroup R1 of f is just given by the functional equation for the function log of absolute value, which is just that. So you just span those guys over Q for any x and y in f star. And clearly, if you take the quotient, you get that B1 of f is just isomorphic to f star. That's the Q in the notations I'm using. And so then we wanted to do this for all other n's. And so we define a map from Q of f. This is a map delta n to either wedge 2 of f star. This is when n equals to 2, or the previously defined group bn minus 1 of f tensor f star. This is when n equals to 3. And the map works as follows. Question? No? So so you take generator x and you map it to either 1 minus x wedge x or to the previously defined x sub n minus 1 tensor x. This is when n equals to 2, and this is when n bigger or equals than 3. So you also have to say what happens with 1. So in this case, you can put, so x here is any element of f, not f star. And if you put 1 here, you by definition get 0. So here 1 goes to 0. OK, so now what we wanted to do, not yet. No. So this belongs to the group which already has been defined by induction, Bn of f. And this is element of the just free abelian group. OK? Oh, yes, of course. Thank you, Richard. Yes, thank you very much. Yes. Now, let's define this finally, this subgroup Rn. So we take any linear combination as before of, but now not of elements of our field, but of rational functions over this field, which belongs to the kernel of this map delta n. And here these fj's are just some rational functions on one variable t. OK. Then if you take any expression like that, then we are going the following things. The expression which lies in the kernel of delta. So we define this Rn of f is generated by the following expressions. So you take sum of aj, and then you put your rational function evaluated at 1 minus same function evaluated at 0. So by definition, Rn of f is generated by those guys when for all elements in the kernel. So let me call guys like that a star. For all elements like that, you take differences of their specializations in 2 different points. These are rational functions, so if this specialization happened to be infinity, you just put 0. It's another part of this definition. And now, after that, one proves that this is what we are looking for in a sense that the classical polylog kills this subgroup in the case of a real, in the case when F is a complex field. So the claim is that we get a map from the group Bn of C, which already defined, to real numbers, which is the analog of log, absolute value, which takes the generator Z sub n. Now, Z sub n means projector of the generator Z to this Bn, and it goes to just ln of Z. And so that this map is well defined.
In the definition of Rn, what field F do you want?
Sorry, what?
In the definition of Rn of F on the left-hand board,
Yes.
and the FJs live in Q brackets T, so isn't this always coming from Q?
That's a good point. So this is because I better take here some A and B. So that's a very good point. So A and B belongs to F. So, but also I definitely want to consider here F of T, and this is certainly what I want to do, not Q of T. So this was a mistake. This is the main point. This doesn't change too much because you can do partial linear transformation, but this is the main point. Thank you very much. It's indeed very essential.
So Bn is it isomorphic to a K group?
No.
Okay. So it's bigger.
No, I mean it's bigger. Yes. So now I'm answering Akshay's question. So the Akshay's question was what it has to do with K groups. So we define complex. That's another definition, which I call polylogarithmic motivic complex. And the complex looks as follows. So it starts with the group Bn of F. Then it goes by this differential delta, which was called delta n before, to Bn minus 1 of F tensor F star. Here it goes again to Bn minus 2 of F tensor lambda square of F star. And you keep going. Then you come to B2 of F tensor lambda n minus 2 of F star. And finally, you come to lambda n of F star. Now, this complex is placed in degree 1, 2, and so on. And so the last degree is n. This complex is defined over rational numbers, but could be defined over integers. So I just, for simplicity, spell a definition over rational numbers. If I would define over integers, then the cokernel of this map would be, by definition, just Milnor K group of F. So you can say that this complex is a kind of resolution of Milnor K group. Now, so this map I already defined. It's written here, where it's written. Basically here. When n equals 2, it's slightly different. Just B2 goes to H2 of F star. And this one is just the previous one, tensor identity, and so on. And now to answer fully actually this question, so I just I did not say resolution. It looks. I said it looks like resolution. I didn't make any claims it is resolution. And my next statement is going to contradict this. Nevertheless, it's a morally true statement, so I'm going to comment on this. It's like a resolution, but not quite. But in a sense, it is. OK. I mean, it's a kind of failed attempt to construct a resolution. So the main conjecture, the first main conjecture about this. And again, this is the old conjectures from a little less than 30 years ago. But it says that for any field F, if you take I-dimensional cohomology of this motivic complex, then they are not zero, but they are isomorphic to Gur gamma n k to n minus I of Fq. So this is equivalence K groups. And this is the Adams filtration. So you take associate some piece of equivalent K group. So there is a better way to say the same thing. The better way to say this is just to say that the complex itself plays a role, that there is a quasi-isomorphism from this complex to our home in DMF, derived category, triangulated category of motifs between Q of 0 and Q of n, because it's somehow the main insight of Bellinson was that one should have such complexes, and their cohomology should be given by algebraic case theory. So now we do have these complexes for quite a long time. So originally it's can be understood as, for example, Bloch's high Chow groups. And then there are definitions by Suslin and Voevodsky modifying all the definitions. And so eventually there is a Voevodsky category here and our home in that category. So the actual statement is that this complex is actually quasi-isomorphic to this R-home. Now, what is special about this? So there are some features. I mean, if you look at this conjecture, mainly, okay, here. I want to stress that there are some features there which tell us that if this conjecture is correct, so if correct, then there are some things that, first of all, this BFN is a kind of smallest possible variance of motivic complexes. So here means the following. So if you look, for example, when n equals 2, definitions of Bloch-High-Chow groups, then we do the following. On a field F, the complex looks schematically like that. Take all the curves here, you intersect them with the faces, and then you take free abelian group Z, so you get a complex. And so basically, the space you consider here is infinite dimensional, the space of all algebraic cycles. If you go to other versions, say, make them even a little bigger. So this one, from this perspective, is finite dimensional. It's, I would say, even one-dimensional, because you only deal with projective line. You take points, free abelian group of the points on projective line. Secondly, the reason we don't have abelian category of mixed motifs is that there is this vanishing conjecture, which says that hi, when I is less or equal to 0, has to be 0. So in this definition, it's built in. So here, hi of whatever, let's say of b, fn equals to 0 is built in, which means that we have absolutely when I less than 0, less or equal to 0. Which means that at this moment there is no hope to prove these conjectures in general, because we really don't know this. This is Bellinson-Sully vanishing, and this is the main roadblock towards motifs. But still, so the difference is that this complex goes very infinitely far to the left, and this stops where it's supposed to stop. OK, but the more important for today's lecture feature of this complex is the following.
Sorry, is it explicit
yes.
between this and the higher Chow complex?
Yes. But the main question is whether this whether you can prove this map is a quasi-isomorphism. I said yes, and this was actually a little lie, because there exists an explicit map on the generators. When you try to prove that the relations go to 0, you get into trouble. So there exist maps for small lamp. In general, it should work, but I'm not discussing this. OK. So then the next thing about them is that these complexes can be extended to any scheme. So if correct, then can be extended. I mean, the definition can be extended to any scheme. So you get motivic complexes for any scheme. And what's important is that if you do this in the case when your field F is just field of rational functions on a variety, so X is a variety over C, then you get explicit regulator map. So you can map this complex B for the field of functions at n to n's Deligne complex of a spec C of C of xn. This is just a statement that regulator map to the link cohomology is exists and explicit. So what I'm saying is that if this is correct, then this gives all regulator maps. But the question is, what do we know about this? And the first statement is that now there are claims which supporting this up to weight 4. So that's the main message. The theorem. So this is the main result. I'm talking about today. That for any field f, there exists canonical map, let me call it C for I, which takes the desired groups k a minus I of f to I-dimensional cohomology of these complexes for this field f for n equals 4 for all i's. And secondly, that these maps are so if you take now any x variety over C, so if you take f as before to be the field of rational functions here, then these are exactly the regulator map. So this regulator, which I said can be constructed here, let's call just regulator, composed with this map on k groups from cohomologies complex to k groups. This is precisely Beilinsen's regulator. So I claim this for n equals 4 for weight 4, and this is was known before for n equals 3, and certainly known for n equals 2 due to the works of Suslin in 1982. So, okay. Now, little comment to this. So, in particular, if you take the special case when you base field of C, then in this case, what you get map from K7 of C to the kernel, to the cohomology of this complex, which is kernel of B4 of C going to B3 of C tensor C star. And this is by the full logarithm map to R. So you see you have complexes still on the blackboard. So if you want to take H1, then you're really talking about the kernel of this map. And so I'm saying that in the weight 4, when n equals 4, for C, if the K7 by general result maps to the kernel of this map, then you can map it to real numbers. And so you end up from K7 of C to real numbers. And the theorem also say that this is a Borel regulator. Now, this implies Zagier's conjecture, so which I can state now.
For another field F, just like in this situation, we also expect this first map not just to be also be an isomorphism.
Yes.
So does that also?
So the main point is surjective. This map is surjective, and then you can. I don't think we claim it's isomorphism, but because this is a question of subgroup, we take quotients. But the main point is this map is surjective. You can settle the definition so it will be isomorphism, but the way I settle it's okay. So theorem 2. So this is Zagier's conjecture, formulated in a slightly different way, but still, for number fields. So it says that if you have standard numbers assigned to the number field, so if this is R1 to plus 2 or 2, then there exist some elements y1 and so on, yr2, which belongs to the kernel of this map delta 4, which sits by the very definition in the group B4 of F, such that zeta F4 equals pi to 4 R1 plus R2 times square root of the discriminant as usual, and most importantly determinant of those L for logarithms evaluated on embeddings of these elements yj. So now if there was a question what exactly is the statement of the Gibbs conjecture, this is a statement when n is equal 4, and you can imagine the same statement is supposed to be true for all n, but known only for small n. Now there is a complement to this, that if you take any y1 so on yr2 as above, killed by delta, then you still have the formula that the determinant on the right-hand side equals zeta f4. However, now there is a little proportionality coefficient which belongs to Q. And the catch is that it could be 0. So you can form this determinant. You always get something proportional to zeta function, but it's possible it could be 0. So the main statement is that there are choices where it's not 0. That's the surjectivity statement. And since I was talking about these complexes for varieties, it's another. I'm not going to concentrate on this, but there are similar results on L function of elliptic curve at the point 4, where E is elliptic curve over Q. All right. So now the question is what all this means. So we started with conjecture on special value of zeta function. Then I reformulated it as a statement about H1 of some complexes for the number field, and so put these complexes into the game. Then the question is what actually happening, and what this complexes, if this conjecture, if this is true, what does it tell us, what extra it tells us about mixed motifs. And so this is what I'm going to explain, because the proof of this theorem goes through this understanding and through corresponding results about motivic Lie algebra. So I'm going to explain.
This is Borel's computation.
Yes. So
similar results on LE4.
There is a statement about you can use some results of balance in order to produce elements in K group, and then you can map K theory to this complex and so on. So there are elements which handle this. And so I actually said, and I wanted to say this once again, that this theorem follows, this is Borel plus theorem 1. Okay? And this is theorem 1 plus something which comes from Walker balancing. All right. Now, then we have two questions. So the first question is, what's new we learn from this? This conjecture A tells about mixed motifs. And the question 2, which I'm going to address, is why n equals 4, or n bigger or equals to 4 case is essentially different. So in order to approach those questions, so I should maybe stop for a second and say that the proof for smaller weights and for weight 4, it incorporates several different things. And the thing which is the simplest to explain is that we need to find some functional equations for some functions related to this game. So what I'm going to do right now, I'm going to basically follow this road, but I'm going to explain motivic picture which leads to that. Okay. So motivic picture. And again, I stress that my main point is that, okay, so you have these complexes, so it's conjectural, they coincides with motivic complexes, which are very big. And so the question is, if they indeed quasi-isomorphic to them, what does it mean from the point of view of mixed motifs? And the answer is that this brings us to some extra yet conjectural knowledge about mixed motifs, which is kind of beyond standard conjectures. And so I want to explain this, what is beyond standard conjectures. So, okay, now you have F is any field. And the first thing is that we, according to Beilinson, one should exist abelian category of mixed Tate motifs. So I emphasize very much that the word abelian category. If I settle for derived category, it exists because it all sits in this Voevodsky DMF, and you can just generate the smallest subcategory closed under extensions which contains the Tate motifs. That would be it. But the conjecture is that we wanted to have a abelian category. Now, and this implies what I said is kind of beyond standard conjectures. Standard, I mean, there are a number of conjectures in this field which we very much believe and which we don't think will break, which follows back to Bellinson and Grothendieck. So now let's see what we have extra. So first of all, I claim that if these complexes calculate what they should, then we have the following general statement which can be formulated without any mentioning of these complexes. So this abelian category of mixed state motifs, I denote this MTF. So the statement then that if you take X groups in the category of the smallest possible mixed category, the category of mixed state motifs, then it's the same as the X groups in the biggest category we have, DMF. Now I'm saying that if this is true, then this has to be true. But this does not imply that. And so the next question is, what actually else we know about, we kind of learned from this. So as I said, conjecture B implies conjecture A, but not other way around, not at all. Conjecture who implies whom? A implies B, but B does not imply A. So let me remind you that we have that if we have category of mixed state motifs, and at this moment we have it only in limited cases when F is a number field or field of rational functions on a rational variety of a number field, but I'm thinking geometrically, so I assume it exists. Then there is a fiber functor omega from empty F to vector spaces, which is a usual thing in this story, which takes a mixed motif here and assign to the home from Q of minus n to gr gamma with respect to the weight filtration of M, W to nm. And you take sum over all n, and this is just a vector space. So there is a functor, fiber functor, and we can define the Lie mixed state motivic Galois Lie algebra as the endomorphisms of this fiber functor, which commutes with the tensor structure in this abelian tensor category. So we get some graded Lie algebra, graded by negative numbers Lie algebra. Now, it is very useful to consider the dual object. So we just take the dual. This is Lie mt of F dot. This is a graded dual, I'll just say dual, to this Lie algebra. And so now this is a Lie coalgebra. Okay. Now the conjecture, which is actually now equivalent to conjecture A, is conjecture C. It tells something about this motivic Lie algebra. So it tells that it has a path. So if you take L where grading is bigger than 1, then this will be some part of this motivic Lie algebra, because this guy is graded by integers which are in Z bigger than 0, including 1, but I take the part which has degree bigger than 1. And so the claim is that this Lie coalgebra, that's a conjecture, is a co-free graded Lie coalgebra co-generated by the vector spaces Bn of F when n is bigger or equal than 2. Now, if you don't like these words co-free, co-generated, and so on, then just cross them out But now you have to pay the price. You have to consider the dual space and generate the corresponding Lie algebra. So it's just tautology, but it's people more used to think about Lie algebras than Lie coalgebras. Okay, so basically it doesn't say that this Lie algebra is free, not at all, but it says that it has ideal such that if you take this, the gap between them is very small, so we know that L1 of F is just a multiplicative group of the field. And so modulo Z, it tells precisely how this motivic Lie algebra of any field F looks like. So it's a free Lie algebra generated by these higher block groups. And now I'm saying that this conjecture C is actually equivalent to this original conjecture A about structure of motivic complexes. And so the main upshot here that when we saying that motivic complexes have the smallest possible model generated by polylogs, what really stands behind this is a conjecture that we know motivic Galois group of this category. And this, huh?
You dotted one of those arrows.
Yes, because I need to formulate conjecture C plus epsilon, which exists. I can state it this way, but I don't want to because it will take a little more time. So there's a little more statement in this conjecture. The conjecture is a little more precise than the one I stated. It tells you also how L1 talks to the higher guys. Let me skip it, okay?
And these block groups
Huh?
have now the kernels of the
What?
I thought that the previous BNs you defined were the pre-block.
What? There's no pre-block group here. I don't know. I mean, okay.
So if F is a number field here, the way you defined B2 was going to be infinite dimensional.
Yes, that's the whole point. I mean, so in this business, there's almost everybody says that the block group is a group which I call the kernel of the map from B, let's say from B2 to H2 of B star. So I don't use this terminology, and I insist that not the kernel is important, but the group itself. Not the cohomology of this complex important, but the complex itself is more important. And so my groups B are very big groups. Okay?
So you are saying that C plus epsilon implies A?
Then they're equivalent. They're literally equivalent. Yeah.
Then the dotted arrow should be the other one.
What? Sorry, what?
The dotted arrow should be the other one.
No. No, these conjectures are really equivalent, so I can explain this. But I didn't explain this epsilon. As usual, if you start telling you what you're not telling people, it takes much longer.
Sorry, can you say something about this freeness? Because the freeness usually comes from some vanishing of x2s.
Yes, but it's not. This is x2s. This is x2s for the Lie subalgebra. So let me tell you the kind of number theoretic element of this. There's a
number field here, right? F is any field.
L is any field, but there is a conjecture of Shafarevich, which says that if you take the absolute Galois group of Q bar over Q over zeta, how you put it, zeta infinity, you take maximum valence tension of Q, then this guy is free, pro-free.
But you're making an assertion for any field.
Yes, yes, yes. So this is like that because here we talk not about the Galois group Q bar over Q, but a little smaller guy sitting here. So they're similar, although none follows from the other, but they're similar.
Suggest there's some analog of this that holds for any field?
There is actually, I mean, this conjecture is a motivic conjecture, so you can deduce from this some statement about the Galois groups. Yes, absolutely. You go to L-adic realization, you get some statement about some Zariski envelope of Zariski state envelope of the Galois group. But I wanted to do it geometrically. Okay, so.
Conjecture C is about mixed state motives.
Yes.
Conjecture A was about X groups in derived category of mixed motives.
Yes.
So are you assuming conjecture B in order to
I certainly assume that this Lie algebra does exist. This assumes that the category, that mixed state category, abelian mixed state category of the abelian category of mixed state motives does exist. We don't know yet it exists for arbitrary number field F.
But then it seems
But for arbitrary field F, sorry. Huh?
tell you something about X groups in the category of mixed state motives.
That's what I said, that X in the mixed state should coincide with X in the huge category.
This equivalence assumes
No, it does not. It does not, but it does not. Let me. No, it's just true as I said that A is equivalent to C. All right. So now let me actually go to some statements how actually we approach to prove this. C C implies both B and C implies both B and A. Yes. All I'm saying is that C is the real statement, and the rest is a kind of derivations of this statement. But still, so let me remind you to talk about this C or whatever. So let me remind you what is a Chevalier Eilenberg cochain complex. It's very well known, but still, of a Lie coalgebra L. So this is just the following complex. So it takes this Lie coalgebra L. Then you go to the second square of this L. Then you go to the second cube of this L, and so on, and you keep going. Now, if your Lie coalgebra, as in my case, is graded, then all this are maps of graded vector spaces. And therefore, what you can do, you can take the part of degree you wish. In this case, I want to take part of degree n. And so I denote this as a Chevalier Eilenberg of this Lie algebra L of degree n. This is a graded Lie algebra. It's just a notation. And one of the reformulations of this conjectures I was talking about is the following one. That if you take this Chevalier Eilenberg complex of the motivic Lie algebra of the field F, I call it MT, then this is quasi-isomorphic to this motivic complex R home and DMF between Q of 0, Q of n. So this is again conjectural statement, but it's just a combination of some statements which appeared on the blackboard before. Just wanted to make it explicit. And now, what do we actually prove? So theorem. This is not the complete proof of the Zagiers conjecture. It's some part of it, but this is a part relevant for the discussion. That for any field F, there is, it's constructed a functorial in F, natural, Lie coalgebra L less or equal than 4. This is just subpiece of weights less or equal than 4 of F, which satisfies, roughly speaking, it satisfying this weight less or equal to 4 conjecture C prediction. And I will write this on the blackboard, what all this means. And the second statement is that if F is actually a number field assigned some is field of functions on a rational variety of a number field, or maybe a little more than that, which I don't want to discuss, but this is a key case, then actually the Lie algebra which we construct is isomorphic to the Lie algebra we wanted. And in this case, this Lie algebra is no longer conjectural because mixed state motifs exist over number fields, for example. And so this Lie algebra is actual thing. It does exist. And so the claim is that there is a canonical isomorphism between them. Now, what is a little more precise statement behind this? So now you're going to see how all these things work together. So what does this tells us about the structure of this L less or equal than 4? First of all, what is L1 of F? So the claim is this is just a multiplicative group of your field, tensor Q. So what is L2 of F? So the claim is that this is canonically isomorphic to this block group. I define this as a Q vector space, B2. Now, what is L3 of F? So the claim is that it's canonically isomorphic to group B3 of F. And what is L4 of F? So you may say that L4 of F is isomorphic to B4 of F, and this is very much wrong. And so what is actually true is that there is exact sequence. So B4 of F goes to the guy which we construct, L2 of F, L4 of F, and it projects to second exterior power of B2 of F. And so the sequence is exact. So this describes how this first four parts of this motivic algebra look like. And I wanted to comment that this is exactly what this conjecture about freeness tells us. Because remember what this conjecture is still here. No. So what it was telling us that we have to consider this Lie algebra L2 plus Lie algebra plus L3 plus L4 plus and so on. And then you have to take the B group, B2, B3, B4, and so on. And you have to co-generate co-Lie algebra. But on a dual language, if you're talking about something which lives in weight 4, you can have now commutators which come from weight 2. And that's exactly what this exact sequence says. That if you dualize this, then you'll see that you have these commutators coming from B2 sitting there. And the most important part of this statement is that the gap between what it should be here and this is very small. It's again generated by projective line. This is somehow the main point of this statement. And it comes with explicit description how this coproduct works here, which I probably skip for a second. Okay? All right. Now let's describe. So what I need to do, I need to describe some vector space L4, which has this structure. And so here is a construction. The first thing that, as usual, so I'm talking about mixed motives, but I keep in mind that I really want to understand something about functions. About which functions? Now there are two functions to think about. One of them is the full log, which is the, and the other one is the Lie 1 of xy, which can be defined again by power series, something like x to a y to b, a cube b to 4, so a less than b. And again, it's a function of weight 4. And so what I wanted to have, first of all, motivic incarnations of these functions. And I want to have this vector space which knows everything about all relations these functions satisfy. And so formally, I said it this way. I said that L4 of F is going to be defined as a certain quotient of Q of F. And this is a guy which talks about us about Lie 4. Plus tensor square, again, of Q of F. And this is a guy which talks to us about Lie 3. And now I want to put here some relations. So let me call them like this kind of R4 of F. And so the main of these relations looks as follows. Actually, there's so we take any 7 points on projective line over field F. So let's call these points x1 and so on x7. Then we consider the following expression. So I write you formula, and then I draw a picture for this. It will be the cyclic shift of the following guy. So I use notation that I use some shortcut. What did you ask?
You want B to the fourth or
I don't understand the question. So I have Li 4 and Li 3 1. So what?
Yeah, you have b to the fourth in the denominator. Is that what you want?
I didn't say anything like that. So I said I defined the subgroup. Hmm? Oh, that's a good point. The weight is 4, so it's 3 plus 1. Thank you. Yes, 3 plus 1 equals 4. Sorry. Because this guy is defined as a sum of x to a divided by a to 4. Yes. So this is a cross ratio. So I have projective line. So I take 4 points. I call them x1, x2, x3, and x4. And I take the cross ratio. And so I call it R. So now let me first of all give you a kind of picture description of the formula which I want to write down. So I know. So I take 7 points. 1, 2, 3, 4, 5, 6, 7. It's just some people easier read formulas, some people easier read pictures. So I don't know who you are. So 1, 2. This is my points labeled cyclically. Then I draw this line, and I notice that I have 3 points here, which will play a special role. And so what I'm doing, I'm drawing a hexagon like that, where I'm missing one of these points. For example, I miss this one. Then I'm going to draw a hexagon like that. So, and as soon as I draw this hexagon, I immediately see that I have 2 cross ratios, because I have the cross ratios here related to this diagonal of this and this one. So I have cross ratio related to these 4 points and cross ratio related to those 4 points. So if you got this picture, so you can read the next formula. So it's 1, 2, 3, 4, comma, 4, 5, 6, 7, 1, and phi is omitted. And this comes with symbol 3, 1. And then it goes plus exactly the same thing, 1, 2, 3, 4, comma, 4, 5, 6, 7, 1, and you omit 6, and minus exactly the same thing, 1, 2, 3, 4, comma, 1, 2, 3, 4, 5, 6, 7, omitted, 1. And so I have a cyclic sum of explicitly given to you literally 1 functions. And you read this from this picture. So, I mean, you take the diagonal to break the symmetry, draw arguments of your function, and then you rotate cyclically this picture. And not that it is 0, but it's close to be 0. Then you plus here a very little thing. 1, 2, 4, 6 in 4 plus some other little thing which I didn't even define yet. And so this is a relation, which means that if you evaluate the corresponding functions, this expression, you'll get plane 0. So this is a functional equation. And I owe you a definition of this guy a minute later. So this is the functional equation for this, which relates both Li4 and this function. I am saying that that's it. So the definition of L4 is rather simple. I mean, if I do want to be on safe line, I should also add here the group of functional relations for logs, which I don't think we need, but we don't yet know how complete proof. We don't yet know proof of this, so I can just add them. But basically, I think that the main point is that there is one very sufficiently simple functional equation which connects these 2 functions, which takes care of the definition of this L4 and about this Lie algebra. So I don't have time to explain to you how Lie algebra structure reads from there. But my point is the following, that if you now ask me how you define explicitly, and this is probably the last thing I'm going to say, the previous like B2 and B3, there are also very beautiful descriptions of functional equations, but this time this is functional equations for dilog and trilog. So that's the last thing I'm going to say. So if you have, for example, the group B2 of F, you can define it sort of similarly. It says this is free abelian group, but generated not by this abstract stuff, but just by 5 term relations, which comes from configurations of 5 points on projective line. You forget one by one them, take cross ratio and put this as a subgroup, and this is known that any functional equation for dialog follows from this. Or you can define the group B3 of f. This is what I did explicitly some time ago. You can take again here Z or Q of f and define some kind of relation related to configurations of 5 points on P2, which is also quite easy to describe. But if you try to do this to B4, you can write this functional equation, some of them, like Kummer wrote some of them, but it doesn't do you too much good. And so it turns out that if you think about the big objects, this Lie coalgebra, then first of all it can be defined in a kind of similar, very explicit, but I would say rather simple way. And secondly, it does the job. So it allows to handle all the questions which appear to the fact that L4 is bigger than B2. And hopefully, so this understanding carries through the high weights. So before it was kind of a roadblock what to do with high weights, where the gap between this is getting bigger and bigger. And so it seems to be that this setup should be carried on, at least for some high n. OK, thank you very much.